Okay, then don't worry, I will restart again. Good afternoon. Just after lunch, I was saying that we have organized a short session to present several technologies we had here in Spain, in the UPM. And the context, just to explain a little bit what is the context of that, is that during this year, we have organized a course on commercialization of technology for researchers working on different research groups that we have considered that they have something that could be interesting. Why? Well, because from our perspective, it's very important that researchers could understand better what kind of things are related to the commercialization process. Because at the end, in our model, it's not possible to transfer everything to other external people, and then researchers said, no, this is not my role. My role has finished with the research, and then I don't nothing to do with the rest of the phases. From my experience and my knowledge, it doesn't work. Then the only possibility is to convince them that they need also to be involved more or less detail in everything related to commercialization. For that, it's important that they could know these kind of things to understand what are the main elements of the commercialization process. In this way, with the help of several companies or entities associated to us and sponsors, etc., we have organized a pilot course on commercialization of technology. And we had 23 or 24 students, into quotes, and I was in fact discussing with Aristides, I don't know how many of them will survive, because probably it is a voluntary process and many of them could disappear in the middle of the course. I was wrong. Nobody disappeared, and everybody arrived at the end. And then as a part of the process, we decided that well, it's not exams, it's not because it's not a formal course in the sense of any kind of curriculum process, but they need to prepare something like a commercial fact sheet of the technology where they were involved. And for many of them, this is the first time they need to write something, not in academic terms, it's nothing related to an academic paper, but it is something to demonstrate that the technology could be useful for the market. And then at the end, we have selected 3 of them, and then the idea is just to give them the opportunity to present what kind of thing they have learned during the course and what is the technology they were working on. That is the idea. Then they have less than 10 minutes. I don't know how many minutes they have. 5 minutes. It's like an elevator pitch, but not in terms of a spin-off, it's in terms of technology. And then we will start with Javier Olea with something related with the infrared. I don't know, Javier is there. Okay.
Thank you.
Even before the 5 minutes.
Thank you, Gonzalo. Good afternoon, everyone. I'm going to present you the technology infrared. Infrared are infrared are silicon-based photodetectors for the visible up to the mid-infrared range. Okay, so what is infrared? Okay, thank you. Anybody, just for being at a certain temperature, emits infrared radiation. So, although we cannot see it, infrared radiation has a lot of information that we can use for certain applications, such as night and thermal vision, process control in a solar cell line, medical sensing, automotive sensing for security of the pedestrian, to detect the pedestrians, security, for example, we cannot see in the visible through the smoke in a fire, but in the infrared we can see through the smoke. So how is the market of the infrared photodetectors? We have analyzed this big company, Sofradir, that is a French spin-off created in the 1986. In 2002, Sofradir founded Ulysse, a subsidiary that had last year a benefit of 50 million euros. In 2007, Sofradir built a new factory to increase the production, and at the very beginning of the world financial crisis, bought Electrophysics, an American company, to enter the American market that is the biggest of the world. in 2011 had about 150 million of sales. That is about 25% of the infrared sensor market. And last year acquired new technology in the middle of the world financial crisis. And the main clients are armies, the US armies, and other companies like TELS, the European Space Agency. So although there are big companies in this market, there are also under-penetrated markets such as the security cameras, automotive, military. It's been said that in the next 5 years, the market will be growing about 23% each year. So there is an opportunity here. What is infrared? Let's compare it with the existing technologies. Sofradir sells infrared photodetectors, very nice infrared photodetector, but have to be cool at cryogenic temperatures. That means cost and handling problems. ULIS, to solve this problem, sells infrared photodetectors that work at room temperature, but the speed is relatively slow. We have this company, NIT, that sells infrared photodetectors that work at room temperature. They are fast, but they are based on toxic material such as lead or cadmium, the same as Sofradir. So this means also cost because of the abundance of these elements. Psionics, that is an American company, has a very similar technology in the sense that they sell uncooled photodetectors. They are fast. They are based also on silicon. So this means less cost, but they have a reduced number of applications, as we will see in the next slide. Infrared, our technology, works at room temperature, is fast, is based on silicon, so very abundant, non-toxic. That means cost and has a broader range of application. In this slide, we see compare the range in the infrared of psionics and infrared. As you can see, psionics is reduced in the infrared range, so this has less number of applications than infrared. So, in summary, the technology is based on silicon. Fabrication is compatible with 90% of the actual technology that is also based in silicon. This means cost. This device works at room temperature, saving also cost, and the detector can be applied for the visible up to the mid-infrared range. These characteristics have been called in the photodetectors field as the holy grail of the infrared detection. And industry have been looking for it for a long time. So what do we have now? We have our lab prototype. We need to get mature to get to the industry and commercialize it. Well, this is infrared. Infrared have been developed in collaboration between the Politécnica University of Madrid and the Complutense University of Madrid, with 2 groups with more than 35 years of experience in the microelectronics field. Thank you.
Has arrived from a research project. Probably they will need more time to become a mature technology, but it's not easy to do this kind of maturation process without the interest of some external company that could be interested on that. And we found that in this case the only solution to create a spin-off. Not necessarily. Probably this type of things could be solved by using other approaches, and just to have a partnership with others in order to put these kinds of devices into the market, because they don't need to become entrepreneurs. There are also many other possibilities, and then we are also interested in exploring other possibilities apart from the creation of the spin-off. Do you have any specific questions to him? If not, we could move to the next one. Okay? Then, thank you very much, Javier. The second one is Gonzalo Sanchez. I don't know. You are there. And he will explain about Vestma. It's not here? You're looking for that. And this is another type of technology. It's related with it's not the civil construction. This is just because he could explain something. Because they are working in the aeronautics school and working on the capturing debris in space. That is the example, and then you have the floor, please. Mike.
So we are not working on capturing, but in the orbiting. So something different. So thank you, Gonzalo, for giving me the opportunity to speak about how can we use a type of aluminum to solve one of the most important problems of the space industry, that is the space debris. After 60 years of space activity, we have now 6,000 tons of object above us, and this includes the upper stage of rockets and dead satellite. So this is now a problem because, as you can see in this plot produced by NASA a few years ago, the number of objects will increase in time very rapidly in LEO orbit. This is because we are now under what is called the Kessler Syndrome. And this is a chain reaction that is produced by the fragment produced by collision of satellite. A collision produces fragment, and this fragment can collide with other satellite, producing a cascade of objects. Of course, this is very risky for an industry that would like to launch about 1,000 satellites the next 10 years, with a cost about 150 billion of euros. The only long-term solution is to have a technology that is able to the orbit to bring back to the Earth the satellite at the end of its life. This technology should be very light. It should be efficient at 800 kilometers, that is the altitude where we have the problem of the space debris. It should have a short deorbit time. It should be simple, scalable, and it would be great if it has some maneuver capability. If one goes to the market looking for this technology, then find two different families of technologies. The propulsive technologies that works because they exchange momentum with a propellant. And here we can find chemical rocket and plasma thruster. Chemical rockets are very reliable, but they are very heavy, so they don't fit this requirement. Plasma thruster, they can be lighter, but they have difficulties with scalability and also with reliability. The second family are dissipative system. And these devices works because a dissipative force appear in a natural way. The sails are a good idea, but they don't work at 800 kilometer height because the air density is very low. So we have to look for a different physics. And what we propose at the UPM is to use an electrodynamic tether. That works because when we have the geomagnetic field, here this magnet, and there is a relative motion with a conductor, the tape tether, you can see what happened. You see, it takes a lot of time to go down because a Lorentz drag appears. And this is actually what can be used to deorbit the satellite. So a few years ago, the European Commission gave 2 million euros to a consortium that is called BETS, that has 7 partners, to develop all the necessary technology to implement this system. This project is coordinated by Professor Juan San Martin, who introduced the BERT tether concept in 1993. The idea is to deploy a long tape of aluminum, about 1-2 kilometers, with a small device here that is called a plasma contactor. So when this device is switched on, a drag force, the Lorentz force, appears in the tether, as you can show in the experiment. So this technology can be much lighter than a rocket. It is passive. It does not require propellant. And they also provide power on board. However, it's always a however, this technology is under development. So we hope that we will reach an RTL about 5 after BETS. At this moment, the consortium can offer 2 products, but of course we are open to investors. The first product is the tether system itself, that includes the prototype, all the necessary prototype to do this to happen. You can see here, for instance, the deployer with the tape here inside, and this is the plasma contactor designed, manufactured, and tested by John Williams in the States. And we are looking for and in Orbit demonstration that will be able to put this technology in a level equal to 7. So we're looking for opportunities, and in this respect, the Horizon 2020 looks very nice for us. The second product is a software called Betsma that has been developed here at the UPM, and this software can be used to do preliminary emission analysis with bird tethers. The software will be registered probably in 1 month and a half, and we will sell the license. So, in summary, the space debris is a very important problem. We need to look for global solution, and we have to look for a technology that is able to deorbit satellite at the end of life. In this respect, I kindly ask to the university and to all of you to bet on electrodynamic tether, that is to bet on bets. Thank you.
This technology is another example of something that has been created with a lot of partners in Europe associated to the framework program. And now in Horizon 2020, the next framework program, innovation is included, is embedded, in fact, into the program, in the sense that demonstration, pilots, etc., should be considered as a crucial part of the new research projects. Then we have considered here at the university that we have a huge opportunity to extend our participation in the framework program in Horizon 2020, not only the work packages related to research, but also in those work packages related also to innovation parts, to pilot, to demonstrators, etc. But the type of partnerships we need to do that is different than from the research part. That's another type of people with another type of interest, etc. And also the software. This is a very specific case where nobody is building up satellites at this moment, but it's an emerging market, and probably for the future, new people will arrive to this conceptually new area, and then the advantage is that we could start here with something, with a new technology to start. That is our basic point. We are not starting from scratch as others, but we start with something. And there are some possibilities. To create a company, probably this is not the best solution. To sell the technology to others, maybe. To work with others, probably better. Anyway, this is the second case. Do you have any question to him? Yeah, please.
The new movie that's probably going to win the Academy Award in America is called Gravity, and it's all about a satellite out of control that destroys a manned space station.
Any other question? No? Okay, then thank you very much. We can, no hands-free. The third one is about the structural fiber sensing from Antonio Fernandez. Antonio is there. And this is another special student we had in this pilot course on commercialization. I don't know, en la documentación están las tres fechas. In the document we have distributed this morning, you could find also a summary of the technologies there. Just to give a reference, you don't need to write anything. Okay.
Thank you, Gonzalo. Thank you, Gonzalo. My name is Antonio Fernandez. I'm from the Department of Aeronautics of the Politécnica University of Madrid. And here I want to present you the structural system that we have developed for try to detect damage inside of complex structures. That is what we call structural fiber sensing. The idea is easy. As complex is the structure, as complex is the maintenance that is associated to this structure, so more complex, more expensive is doing this maintenance. Aside from the School of Aeronautics, obviously, the example in the aircraft industry, the commercial and military aircrafts spend about $75 billion per year just in maintenance. 9% of them is for structural maintenance. Also, civil structures like bridges, big bridges here in Europe just spend 5 billion euros per year just for maintenance. Again, big numbers, a big problem also associated. Also for energy, the wind energy market that is also emerging. Here you can see offshore turbines that have the big issues that are not easy to reach for making all the process. So at the end, need to be developed any kind of system that can be actually that can control remotely the appearance of damage, and in case of something fails, just send a signal to an operator and change the condition. As you see, these three areas are very different materials, very different structures, very different from each other. But, however,
Say it ain't so, Jeff.
All of this structure, as you have seen, has made a strong sound before the final collapse has appeared. This at the end is made by a structural wave, an elastic wave that is propagated all through the structure, like the one that we can promote just knocking a structure, but this was promoted by the damage opinion or just by the damage growth. This is something easy to detect. Maybe you can say we don't need a specific technique or a high technology to detect that. Yes, we can do it with a simple microphone. This is true. This is a usual way to do it. In fact, this is what we call acoustic emission. But it has a problem. Cabling, and at the end, how to manage the signal with a sensor that is completely omnidirectional sometimes can be so difficult. In fact, no one of these techniques has been implemented in big structures and complex structures as the one that we see before. The solution at the end will be simple fiber optics. The fiber optics that I don't have with me because most of you cannot see it, is in the expositor out, is just 0.2 millimeters of thickness. So at the end, don't introduce too much weight and can be easily implemented in all the structure. And even we can go further. One kind of fiber optic sensor, the fiber black ratings, can be easily engraved along the full fiber. So at the end, we have multiplexing, high multiplexing capabilities with a huge number of sensors just introduced in a single fiber. So the idea appears several years ago when I was making the PhD degree, and in 2009 this was the full system that at the end joined the two big capabilities that we have: higher acquisition frequency and a very high resolution. Currently, just a couple of systems like this are capable to do that in the world. But we have gone further. Our system at the end was mounted in a box like this that at the end can be easily introduced in a structure for real-time monitoring, and at the end change the time-shifted time-shifted monitoring that we have currently in the structure, stopping the structure from time to time and checking that if everything is fine, to something that at the end just can advise us when something strange can happen. This is one part of the system. The other one will be the software. The damage at the end will generate this wave that propagate through the structure, and we can get this signal with this hardware. But the idea, what we have developed also in the department, is a software that at the end get this signal and can generate easily a map to detect the damage position in even very large structure. So the advantages are a lot. Comparison with the traditional sensors. Most of the advantage is related with geometry. It don't introduce too much weight. It can be easily integrated. So at the end, all the problems that appear with the traditional electric system can be easily solved with the fiber tracker. Just for finishing, here I show you something that clearly clarifies whenever question you have. Here is maybe the two most, let's say, priceless investment that we made in Spain that obviously need to be played, need to operate to at the end recover some of the budget that it would initially cost. So it's the same for a structure. For a complex structure like an aircraft, that more or less it takes 30 kilo euros just to keep in land and not fly. It takes a lot of money. So keep this money back can be easily solved or can be increased this time just using this solution, the optical fiber sensing, for at the end try to improve the operational time of this approach. So that's all. I hope more or less you see more or less the system that we have developed and the possible applications that obviously start. Thank you.
Well, thank you. Do you have any question for him? No? Here this is another case, because could you put the slide with the box that you have developed in 2009, and then this is 2009. This is not a box. This is a typical thing that, well, the project has finished and here is something, and you could demonstrate that, well, okay, the concept is okay, it's running. Then the second part is one, is just, well, it's not the final product, but at least we did the effort to create something closer to the market. It's something to be sold as is. Probably no. Probably we need also to have a third part, and then to move to the product industrialization, the productization, if you like. I don't know in Spanish this word exists, but anyway, and to create this product. It's not the commitment and the responsibility of universities to have the final product to that. But at least we need to arrive to something like that to demonstrate that these kind of products are possible, and then to have a partners, industrial partners, to be able to transfer this kind of technologies. Then the short information you have here. This one, but anyway, it doesn't matter. You could find in the documents we have distributed this morning. It's just part of the first catalog of UPM technologies that we have invented, we have created. In fact, we have identified more or less 60 technologies at this moment. All of them described in fact sheets like that, explaining the technology solution, the areas of application, the market, the potential market, competitive advantages, and also the status of the technology at what is the development level. We have 60 of them. And then probably the deal flow will have 10, 15 more every year. What to do with them? To create one spin-off? Probably he's not interested on that. You see the face? No, not at all. What to do? To put this box just on a shelf and to say, oh, we did that in 2013. And to start a new project, not the usual behavior. Or just to find a new research project even before finishing the previous one. Or to do other things. What is our responsibility as a public university? Just to forget it? And to start again? From scratch? With other things? Or try to do something? My feeling is that we need to do something. And this is the only way that we're here. Trying to find ways, lessons about the mechanism and new avenues for doing something new with this kind of results. Thank you for your introduction.